Okay, so a rough sketch of the phase portrait. Well, the phase portrait is when you just trace out some solutions from your direction field. So my phase portrait is going to look something like this. You just pick some initial conditions and sketch the solutions. And the initial conditions you choose are arbitrary, right? So you can choose any initial conditions, sketch out the solution curves, and you just sketch enough so that you can get a sense of the quality of all the different solutions. And in this case, they're all solutions that just increase or decrease forever. Okay, so mark the point on the phase plane which represents x of 0, y of 0. Okay, well, time is not a factor in this picture. This is just the x, y plane. So we are just looking for the point 1, -2. 1, -2 is the x and y coordinates when time is 0. So we plot the point 1, -2 right here. And then draw the solution curve in the phase plane that satisfies that initial condition. It's that one. So using our solution curve in the phase plane, sketch on one set of axes, x of t and y of t that satisfy the initial condition. All right. So this is t for time. I'm going to sketch x of t. What happens to the x coordinate as time moves forward? So here's my initial condition at 1, -2. And then you imagine the point travels along this line. And that's time, is that this actually has movement. So this point is just traveling in the direction of the direction field over time. And as time goes by, what happens to the x coordinate of this point? Nothing, right? It always stays at 1. As we travel along this line, we get to like 1, -3, 1, -5, 1, -10, right? The x coordinate never changes. The x coordinate is always 1. So if I'm going to sketch what happens to x, it starts at 1, and it just stays there. So this is my graph, x of t. All right, so now on the same set of axes, I want to sketch what happens to y as it follows this solution curve in the xy plane. Okay, so y starts at -2. That's my initial condition. Y starts at -2, so I'll put that down. -2. And then what happens to my y coordinate as it follows this solution curve? It decreases. Yeah, it gets smaller. So we don't know exactly how because we can't see time in this picture, right? It could be linear, could be exponential. We just know it decreases. Because the arrows are getting bigger and bigger from the direction field. Yes. Yep. Good point. So we know it decreases faster and faster from the vector field. And we lost that information when we changed it to a direction field. But it does decrease faster and faster. And I know that if I went backwards in time, it would be approaching 0, but it would never cross 0 because 0 was this point where there was no vector. So it can never cross 0. So if I were to go backwards in time, it would approach 0. And I know it decreases faster and faster, so it probably does something like this. And then it could come up this way if I reversed time. So it looks like a exponential decay. So this one is y of t. Integrate what? The y prime function? Oh yeah, because this is what we call a decoupled system. Yeah, so we could say 1 over y dy equals dt. So you could solve it, but it's not y squared, right? It's going to be e to the something. So y of t equals k e to the t. And then I would use my initial condition to find k, which must have to come out negative in order to get my function to look like this. We can let's see what happens. If we find k, y of 0 is -2. -2. So my actual function is y equals -2 e to the t, which has the shape of the quality function that we graphed. And this one you can solve also. That one has to be, if dx dt is 0, then x of t has to be a constant, right, if the derivative is 0. And then figure out what constant it is by using the initial condition. So this is called a decoupled system of equations because you can solve each one separately using separation of variables. But for the purpose of this class, we just wanted to sketch some qualitative solutions. All right, let's do one more. So get another system of differential equations. We want to write it using vector notation. So we're going to have p prime equals y1. Or if you like to write it horizontally, you can write it horizontally too. Okay, so we want to sketch enough vectors to get a sense of it. So y comma 1. So for every point, we're going to plug in the y coordinate for y and the y component of the vector is always going to be 1. Yep, dx dt is y, and dy dt is 1. So this is always going to be x prime, y prime, your vector field. Yes, because that's how I defined dx dt equals y. Yeah. Okay, so it's 0, 0. Plug in 0 for x and 0 for y in here. So I get 0, comma 1, which is a vector that points straight up. Unit length. At 1, 0, 1 for x, 0 for y, I get 0, comma 1 again. In fact, all along the x-axis, I'm going to get 0, comma 1. Right? Yeah. All right, so let's try 0, 1. So if I plug in 0 for x, 1 for y, I get 1, 1 as my vector. So over 1, up 1, and that's how I plot my next vector. And then let's see if I plot a vector at 0, 2. I'm going to plug in 2 for y, so I get 2, comma 1, which would be over 2, up 1, and that's my next vector. Let's try 1, 1. So plug in 1 for y, and I have 1, 1, so I go over 1, up 1. In fact, anything with a y coordinate of 1 is going to have this same over 1, up 1 vector. And anything with a y coordinate of 2 is going to have this same sort of less steep vector that looks like this. Getting kind of messy. Maybe I'll do a couple negative ones just to get a sense of what happens below the x-axis. So let's see, 0, -1. 0, -1 would be -1, 1. So I would go left 1, up 1, and get a vector like this. And these would all do that. And at -2, I would have -2, 1 as my vector field. So I would go left 2, up 1, and I'm going to have all vectors that look like this. So you can kind of get a sense of what's happening now, even with this really rough sketch of the vectors. If I were to trace in a solution, it probably is something like that. I'm not going to do the direction field. I don't feel like it. Just shorten the arrows. So a rough sketch of the phase portrait. So that's where you just trace in some solution curves. So my phase portrait's going to look something like this. Where you put in as many solutions as you feel are necessary to capture the quality of all the solutions. All our solutions look exactly the same, so a few is fine. They're all this curve that goes in a clockwise direction. And this is x and y. All right, so mark the point on your phase plane that corresponds to 1, -2. So over 1, down 2 might be like right here. And the solution curve that goes through it is going to look something like this. I want to use that solution curve in the xy plane in the phase portrait to sketch solutions x of t and y of t. So here's time. I'm going to track what happens to the x coordinate as it follows this solution curve. So it starts at 1, x coordinate starts at 1, and then it travels left until it gets to something negative. We don't know what that is exactly because this is a qualitative picture, but it gets to something negative. Negative something, comma 0, right, is the y coordinate. Yes. Because of the arrows in the vector field. Yeah. So my x coordinate starts at 1, it gets smaller and smaller and smaller. At some point it hits 0. 0, I don't know the y coordinate exactly, just that it's negative. And then x becomes negative. And then x starts increasing again. It gets bigger until it hits 0. And then it just keeps getting bigger and bigger. So we're just tracking what happens to the x coordinate as it travels along that curve. So it starts at 1 over here. At time 0, my x coordinate is 1. And then it gets smaller and smaller as it travels this curve. X goes from 1 to 0, it's getting smaller, and then it goes from 0 to something negative. No, because we only know this is only a qualitative picture. Yeah. I think I knew for sure because I had a computer draw my vector field. So when I sketched 1, -2, it clearly went negative. But you wouldn't know that if you only drew a few vectors. Okay, so my x-coordinate, it gets smaller and smaller until it hits 0. Then it gets negative, right? Then it comes back to 0, and then it just gets bigger and bigger forever. So these are the two places where my x-coordinate is 0. This is the place where it hits its smallest place, and then it just gets bigger forever. Okay. So now we're going to do the same kind of analysis where we follow that point along the solution curve, but this time we're going to sketch what happens to its y-coordinate. So my y-coordinate starts at -2. Green. Starts at -2, and then it gets bigger, right? It gets bigger and bigger and bigger until it hits 0. And then it just continues to get bigger and bigger and bigger. So my y-coordinate is always increasing. And it hits 0 at the same place that my x-coordinate hit its minimum. When my x-coordinate was the smallest is when my y-coordinate hits 0. So I go back to my sketch here. So at this t value, when my x was the smallest is when my y is 0. So I know I have this point, and I have the starting value at -2, initial condition. And we don't have any information about the speed at which y increases. So this could be a straight line. It could be like the cubic looking thing that I drew in the answers. We don't know exactly what it looks like, but we do know that y is 0 at the same place that x is its minimum. We know it goes through -2 because that's the initial condition, and that it is always increasing. The speed, sure, yeah. Yep. It's tough when you're doing it by hand, yes, but you can do that. We could use the length of the arrows. So what do you think? Is it getting a little clearer? Okay. So I think a good thing for you to do would be to work on number 6. If you haven't already, do your sketch of number 6 here, because it's similar to what we were just doing, and then we can start today's stuff. I'm going to have you do lab 2.2 and lab 2.5 together as your second project. When will that be due? So it was originally set to be due on Friday the 15th. Let's do, yeah, that's this Friday. That's too soon. Oh, right. And then we have a short week when we get back. I don't know. I only have Monday and Wednesday, the 25th and the 27th. Oh, no, there's a Friday. What am I thinking? Okay. No, no. Well, I'll figure it out. I'll let you know when it's going to be due. It won't be due this week. Okay. Wednesday, the week we get back from spring break, is fine with me. Okay. You still have a couple days. Okay. Okay, so remember we talked about the frictionless harmonic oscillator last class. So we have this mass on the end of a spring, and The only forces acting on it is the force of the spring. Okay. And we derived this differential equation using Hooke's law and Newton's second law of motion, the force equals mass times acceleration. We used the two of those. We came up with this differential equation. But the system is frictionless, and this is not a realistic situation, because this would cause perpetual motion that just goes on forever, and it was a periodic solution that represented displacement of the mass. It just moves back and forth forever. To make the model more realistic, we're going to add a term for the damping force of friction, or any damping force. So actually, friction is a really kind of subtle and complicated thing. So rather than try to model exactly friction, we're just going to smush friction and all the other damping forces into one damping term. Okay. So the idea is, like friction, a damping force is going to slow the motion, dissipating energy from the system. So the mass starts moving, but then the displacement's going to get smaller and smaller because friction is going to slow it down. Okay, so we're going to assume that the damping force is proportional to the velocity of the mass. Does that make sense physically to say that the faster the mass is moving, the more friction there is, slower it's moving, the less friction? For the mass, what? Well, yes, but the mass is constant. The value of the mass does not change for any given system. The mass is just a number, right? Yes, like air drag, or if you're like a piston with oil, right, that slows it down as it's moving, right? So it's not necessarily friction. We're just sort of lumping all damping forces together. Yes. For small velocities, it makes sense? Yeah. Yeah, so sort of like the faster it's moving, the harder the damping force works to slow it down. So yeah, that makes sense. Okay, so if the damping force is proportional to velocity, right, then I could say, okay, well, we'll call it, the term would be, I need a new constant that's not K or M. B, let's do B. So B times the velocity, and the velocity of the mass is y prime, the derivative of displacement. And it should be negative because it's slowing things down, right? It's working against the force of the spring. Uh-huh. Well, what we want is the displacement to approach zero, right? Which would be a place where there's no tension or compression. That would be where the velocity is. Well, right. Eventually, it'll be at zero there because the damping forces go there. True. Yeah. In time, yeah. But yeah, so I'm trying to write a term that just expresses damping force is proportional to the velocity, right? So yeah, I could call it 1 over b if I want. It's still just a constant, right? Yeah. Yeah. So I'm going to add this term to my differential equation. Y double prime. I have my initial term. This is the force of the spring, negative K over M times Y, right? So the force of the spring is proportional to displacement, right? So the spring applies more force if you've extended the spring really far or compressed it really far in. And then we have this other term that's proportional to velocity, the damping force. Do I have to divide? Yes, I do. I do, right, because the original equation, sorry, when I derived it, was that force equals mass times acceleration. Force was the force of the spring. We got that by saying the force of the spring is proportional to displacement, and acceleration is y double prime. And then force also now has another term acting on it, the damping force. So now I have two forces, damping and the spring force equals mass times acceleration. So then I would just divide both sides by m here to get y double prime by itself. So y double prime equals negative k over m times y minus b over m times y prime. So we generally simplify this equation by calling k over m and b over m constants. We just rename them as p and q. And I move them to the other side. So I get y double prime plus py prime plus qy equals 0. So if I want to convert this to a second order differential equation, remember you let y prime equal v, so that's your first equation in the system. Y prime equals v. And then v prime would be y double prime. And y double prime is negative p y prime minus qy. Oh yeah, instead of y prime, I should call that v. Thank you. Does that make sense? All right, so there's my system. Now I have a system of second order, of first order equations. So I would like to be able to study some solutions to this ODE. So we're going to have to try to guess some. Okay, so we're going to choose some arbitrary values of P and Q just so that we have something to work with, something to guess with. So we're going to use y double prime plus 3y prime plus 2y equals 0. And a solution y of t would be a function whose second derivative, right, y double prime, can be expressed in terms of y and y prime as negative 3 y prime minus 2y. So the second derivative has to be able to be expressed in terms of a sum of its first derivative and its self. So what kind of functions come to mind when you're thinking, okay, I want its second derivative to equal its first derivative plus itself? E to the t, because it's got its own derivative. It is its own derivative. So e to the t comes to mind. So we're going to guess that maybe there's a solution of the form e to the st. S is just a constant. So let's check and see if we can make e to a constant t work. Okay, so I rewrote the equation here just so we could see it. So we've got y of t is e to the st. And I have to see if that makes this equation true, if I can use that to make this equation true. So y double prime plus 3y prime plus 2y, I have to make that equal 0. So y of t equals e to the st. What does y prime equal? se to the st. And y double prime, s squared e to the st. So now I'm going to plug in y double prime and y prime into the equation, see if I can make that equation true. There's a choice of s that will make it true. So y double prime would be s squared e to the st plus 3 y prime, which is s e to the st, plus 2 times y, which is e to the st. If I can make this equation true, if I can make that equal 0, then I have found a solution. So let's say I think I'm going to factor out e to the st. So I'm going to have s squared plus 3s plus 2. Uh-huh. Yep. So I've got two things I'm multiplying together. The answer is 0. So one or the other has to be 0. When does e to the something ever equal 0? Never, right? It's never equals 0. And then I have a quadratic, a simple quadratic I have to solve. When it equals 0, it factors to, yeah, s plus 2, s plus 1, which means s equals -2 or -1. So I found two s values to make this equation true, using e to the st as my solution. So I have two solutions that I found. Y of t equals e to the -2t. That'll be y1 of t, and y2 of t, a second solution, is e to the -t. Two solutions. Now, both of those solutions, as t goes to infinity, what happens to y, the displacement of the mass? It approaches 0. Does that make sense? Yeah, because I have a damping force that's now slowing the motion. It's eventually going to come to rest at 0. So these should approach 0 as time goes to infinity. Okay, so before we had damping, our solutions were sinusoidal, right? Because the motion was perpetual, always moving back and forth. We had to use a sinusoidal function to model it. Now we can use an exponential decay. So here's a direction field for the system. I created it using WinPlot. We want to sketch the curves in the plane that correspond to our two particular solutions we discovered. So how do I do that? So my two solutions, maybe I'll write them down. Remember, y1 was e to the -2t, and y2 e to the -t. Yes, so we have to get the initial condition, and then we can just trace the curve. To get the initial condition, plug in 0. y1 of 0 is e to the 0, which is 1. And y2 of 0 is e to the 0, which is also 1. So this is so this is my system where y prime was v. What to label my axes? Sorry. There is no x though. I have y and v. Right, but this is the vector field. The time is not in here, right? Time is not in the vector field. This is just y and v, right? When we had a system of x and y, it was x and y, and times doesn't show up. When y is small, v is big. So no, it's definitely not t. No. Y is position, V is velocity. Yeah. Yes, I think you're right. Yeah. So this is what can get confusing also about creating a vector field. Using WinPlot, right? Because WinPlot only takes x's and y's. So you have to change the variables here. And WinPlot always wants you to write x prime equals and y prime equals, right? So you have to go, okay, well, x prime equals the other variable y, because here we have y prime equals something. It's the other variable. And then v is representing our y. So I have negative p x minus, no, v is y. There we go. I know, it's kind of crazy. So we have to let y be x and v be y in order to change the variables. Yeah, no, it won't work. Why not? Oh, okay. This is the field for this differential equation. So I said, do we write it as a system? We never did. Okay, so let's do that. So y prime has to equal v, which means that v prime, which is y double prime, is negative 3v minus 2y. So my vector field, right, when I write this as a vector, which is the first thing that we did in all the activities last class, we said, well, p prime would have to be v negative 3v minus 2y. X prime, y prime. So I guess maybe this is v. No, I think it's the other way. Yeah, position velocity. So yeah. Yeah, so that's upside down. Ooh, I'm gonna have to think about it. So at any rate, I'm pretty sure that that's y and v. And I have my initial condition, right? I know my initial y's, but I need my initial v's, right? Because this doesn't have time in it. It has position and velocity. So how do I figure out what my initial velocity is? Yeah, I know the derivatives, yeah. So y1 prime of 0, right? If y1 is e to the negative 2t, then y1 prime is negative 2 e to the 2t. So that would be negative 2. And y2 prime of 0 would be negative 1. So my initial values are going to be y1 of 0 is 1, and v1 of 0 is negative 2. So 1, negative 2 right here. And it goes like that. And then my other solution is going to be y2 of 0, which is 1, v2 of 0, which is negative 1. So we've got 1, -1 right here, and it also goes into the origin like that. Right, because no, it's never gonna speed back up unless we introduce another force into the system. Yeah. It is? Right. Yeah. Yeah. So our solutions that we found are on straight line curves directly to the origin. But yeah, there are other solutions. We don't have the general one. We just have found 2 particular solutions. Yeah. Nope. Because if you think about the mass on the spring, if the damping force is strong enough that it's just slowing it down, right? The origin stands for at rest. Displacement and velocity are both 0. It's not going to ever speed back up again unless we put another force into the system. So just using the spring force and the damping force, two things that could happen are it could go straight to the origin. Slows right down. All right, so I have a little practice for you guys. Now, keep in mind that this is not necessarily, the signs are a little bit different, right? So this is not necessarily the damped harmonic oscillator. It's just an equation that has a similar form. Okay, so